The broadcast is now starting. All attendees are in listen-only mode.
Hello, good morning, everyone. Welcome to another series of Altair webinar. Today, I'll be your speaker. I'm going to introduce you guys to SimSolid. I'm going to be talking about the workflow in SimSolid and also the benefit of using SimSolid for your design studies. Right. So before we start, just want to make sure everyone is hearing me clearly. Can you guys just raise your hand if you can hear me loud and clear? If you can hear me loud and clear, can you just raise your hands? All right. Okay. Okay, good. Good. All right, so let's start. So a bit about myself. I am currently a application engineer at Altair, Malaysia. And my main task is to conduct trainings specifically in structural simulation and also to help customers adopt our simulation in their product design stage. Right? Before this, I was with an engineering consultancy company, and I spent 8 years there helping the automotive OEMs, right, to simulate their products or their vehicles in the field of strength, stiffness, NV, and also durability. Okay. So a bit of house rules first before we begin. All of you guys will be muted, right? Because I'm going to record this webinar. So, but if you have any questions along my presentation, you can just type in the chat box. And at the end of my session, I will open the mics. And you guys, if you have any questions, you can talk to me. Just raise your hand and I'll unmute you guys. Okay. And throughout this webinar, there'll be some polls so that you guys can vote on a certain question that I'm going to ask. So, right. So just before we start, I just want to check. I've actually shared some handouts on this webinar. Can you guys see the handouts? PDF handouts? If yes, can you just raise your hand? You guys, there should be 3 PDF handouts. All right, so you guys can see it. Okay, good. Right, don't worry about handouts. I'll talk about them later during my presentation. All right, okay, good. Right, so let's start. Okay, so if you guys are familiar with finite element analysis, you probably will do something. It probably starts with this, right? Creating the mesh model. And having 8 years of experience in the field of simulation, I can tell you guys one thing. That meshing is very complex and it's very time consuming, right? If you guys are doing simulation yourself, you will probably agree with me that meshing will probably take up about 40 to 50% of your time to create a model before you can even get the results, right? So meshing is very complex and time consuming. So what if this is your model, right? What if your model is as big as this? Oh wait, Sorry, I think you guys didn't see my slides just now. Let me just go back. Okay, so yep. So meshing is very complex, it's very time consuming. If you have a model such as this, very large assembly models, and probably going to take a long time to prepare your mesh, right? So, and what if your model is as big as something like this? All right. So what if this is your CAD model? You have such a big assembly like this. How do you go about it, right? How long will you take from CAD, right? From the designer when they hand you over the CAD, how long will you take to produce the results, right? And can you perform upfront design simulation, meaning that can you, as fast as the designer change the design, can you immediately give a result, right? And do you have to do all the simulation? As in, if you are doing simulation, do you have to do it all? Or actually, can the designers help to do some of the simulation, right? And ease some of your burden, right? So actually, this is a actual CAD assembly. Is a stage wagon in Wuhan, right? So this assembly actually consists of about 7,000 parts, and it actually just took 60 minutes to set up in SimSolid, and also just took 30 minutes later to solve it on just normal CPU, right? Not even GPU or high performance computer. It's just on normal desktop CPU, right? And most of the time, according to this survey, 79% of new products actually miss the launch date, right? If you're in the product development team, you probably know this, right? There'll be delays and delays. And which each delay, you actually tend to reduce the number of sales, right? So there are sales loss to being late to the market. There are sales loss from being late to launch. And because you launch it late, you probably need to launch another new design. So the current design probably have lesser time to be in the market. So you get sales loss from the lesser time in market as well. So I think you will agree with this, that reducing time to market is actually one of the most important factors in determining whether we get our actual return. And how do we change this? How do we improve ourselves so that we can actually get products to the market faster? We cannot just be doing the same things over and over again, right? We need to do something new. And SimSolid here provides you a new paradigm for simulation, right? We give you a platform to actually perform simulation-driven design very early on. Why is this possible? Because this SimSolid is a structural simulation that operates directly on original unsimplified CAD, right? So you're not required to simplify your CAD assemblies. Just bring up my pointer. So you're not needed to simplify all your CAD assemblies, and we are still a finite element solver, but we do not use mesh, right? So this is the specialty of SimSolid. So we do not need to create mesh, so you actually save a lot of time in your model build up, right? And we can actually provide results within seconds to minutes. no matter how big is your assembly. Right, so before we go on here, just want to get some answers from you guys. How many of you guys have actually used SimSolid before? Right. So you guys should see a poll and you can vote on it. Have you heard of it? Have you tried it? Are you using it? Okay, most of you have heard of it, but not using it. Oh, I see some users. Good. Okay. Right, so I'll give you guys a few more seconds before I close this vote. Right, closing this vote in 5, 4, 3, 2, 1. Right. So most of you guys have heard of it but never use it. Then yeah, some of you guys are just hearing this for the first time. So I'm glad that some of you are using it. Hopefully you can give me some feedback whether it's good or you have some difficulties. I'll be very delighted to help you guys out. Right, so let's just continue. Okay, so here, what's the benefit of using SimSolid? The first one is because we eliminate the most time-consuming task, which is to simplify your geometry and then to mesh it. We actually help you reduce your product development time cycle, right? So with SimSolid, you can actually reduce the most two time-consuming tasks, which is cleanup here and also meshing. Reducing these two will actually give you more time later on to do post-processing on your results, right? After you run the simulation, you can actually do post-processing and come up with a better design compared to, let's say, if you're given 1 week and you already use 3 days to build up the model, and then probably to run it, probably take another day, and then you only get 1 more day to produce your report. So with SimSolid, you can actually just do this very quickly. Maybe the first day itself, you already can get the results, right? So you actually get more time to analyze and more time to come up with a better countermeasure. And SimSolid, we give you the capability to simulate what is traditionally not possible, right? So if your model is very large, traditionally, maybe you probably take a longer time to simulate, or even if you're using some CAD simulation tools, you probably will not be able to simulate some complex geometry like this. But with SimSolid, we give you the capability to do so. So you can actually analyze more and you can actually get a better result, right? So we work with complex parts and we work with large number of parts. And if you have multiple connections, we work fine with that as well. And SimSolid is a true enabler of simulation-driven design. So we give you the capability to simulate your design very early on, right? So if the designers have designed some assemblies for you, you do not need to wait for you to complete the meshing and modeling, right? So you can actually straight away use SimSolid to get a quick feel of what or how the model will perform, right? Very early on, right? And if it's not right, you can just go back to the designers, change or tweak something, change some parts, and then rerun it again. So SimSolid gives you the capability to perform very fast simulation, and then you can actually give very rapid feedback to the designers, right? So, and it's not here to replace the traditional finite element analysis, right? So the traditional finite analysis can still remain here, but what you actually do is, if you use SimSolid at the very beginning in the concept development stage, you can actually churn out better designs, which then later on can ease the burden of the traditional finite element analysis, right? So we are here to complement the existing finite element solvers, right? And we are not here to replace them completely. Okay. So what can we do in SimSolid? Here are some of the simulation capabilities in SimSolid. We can perform modal analysis, we can perform linear statics, and we can even perform non-linear statics. So if you have non-linear context, you have non-linear materials, non-linear geometry, we can actually do it here in SimSolid as well. And we have the capability to perform frequency response, random response, transient response, right? All these are possible. We can also do thermal analysis, and then we can use the thermal load to actually perform thermal stress analysis, right? We have initial relief, we also have bulk pretension, and in new feature, we actually have a linear superposition. So you can, let's say you have two linear statics simulation, and you want to combine them, we can do linear superposition as well. Material-wise, we can work with elastoplastic material, isotropic material. You can create your own material. We have a library of materials inside. If you do not find your material there, you can actually add your own material as well. So connections-wise, we can create multiple connections, ranging from, if you're talking about contacts, we have bonded contacts, sliding, separation, bolts. We can simulate bolt connections, spot welds, seam welds, bushing, rivets. All these are possible in SimSolid. And of course, the results, typical results we can view. We can look at displacement, stress strain. If you're interested in looking at the bolt reaction forces at the bolts, we also have that. If you're running for modal analysis, even look at modal participation factor, we also have that. So all these results are available in SimSolid. Now, just a little bit technical background on how SimSolid works, right? So, comparing it to traditional finite element analysis, right? So your traditional FEA will actually use elements. So probably you create tetra elements, quad elements, hexa elements. So all those, we actually break down a part into smaller elements represented by tetra, hexa, or quads and triangles and so on. So, but in SimSolid, we don't break them down into such small elements, right? So imagine your table, right? Imagine your table. Let me just draw this. Okay, so imagine if you have a table here. Excuse me for my drawing, it's not very good. So imagine that you have a table here. The entire tabletop can be considered as a one element per se, right? So we don't break this entire table into small tetra elements or hexa elements. We can break them down in, probably here we can have 5 elements, one element to represent each legs, right? And then one element to represent the table. So I say element here is just for you to imagine. We don't actually use elements, but imagine that we can actually break down into these few elements. So with fewer elements, you definitely have already fewer equations to solve, right? And in the traditional finite element analysis, we actually need to create degree of freedom equations to represent each node. So you probably at each node of a element, you have 3 degrees of freedom equations to represent them. But in SimSolid, because we have already fewer elements and the degree of freedom equations are no longer placed at the node, right? At the node of the element per se, we actually place the degree of freedom probably to represent this entire region, right? So we call it region, arbitrary regions here. Now with this, we actually get to create fewer equations to solve, right? So remember I said SimSolid is still a finite element analysis. We still need to solve the basic static equations. But now we have fewer equations to solve here in SimSolid because we don't use the traditional elements here, right? And another thing is that another difference is in traditional finite element analysis, the boundary conditions are met exactly. So if let's say for a simple static analysis, you have probably a SPC or single point constraint here. This constraint, the displacement will be always 0, right? In the traditional FEA, but in SimSolid, here our boundary conditions are met approximately, meaning to say that you will see some slight displacement at the boundary conditions. So it probably will have will be in the region of e to the power -7 or -6. So it's engineering 0, right? So we approximate the conditions at the boundary conditions. And in the traditional finite analysis, we probably use very low degree of polynomials to represent the shapes. So it's either we use a first degree or second degree, or in another sense, first order or second order elements. But in SimSolid, we use higher than that, right? So that's why that's how we get better accuracy. Okay. Now here's a walkthrough of how SimSolid is working in the background. When we read in your geometry, we actually convert your geometry into faceted volumes. Now, just to let you guys know, we only work with solid geometries, right? So it has to be solid in your CAD. We cannot read. If you read in surfaces, it will not appear in SimSolid. So we need to work with solids here. And once you read the geometry in, we actually convert it into faceted volumes. Okay. Let me just check for a moment. Just see if everything's okay. Right. So, yep. Yeah. So we convert them into faceted volumes, and what's next? The user will actually, before the user actually do anything, we actually the algorithm in SimSolid will actually detect and classify geometry, right? So it will detect automatically where are the bolts, which parts are the bolts, which parts are the nuts, and if you have any springs, you will detect and classify them, right? If you have thin sheets, you'll put them in a different category. If you have holes, they also specify them as well. So classification here is done automatically, right? You don't need to worry about it. Next, what you need to do, the user will just need to create connections. Okay, so all the different connections here, with a very simple click, right? Just 1 or 2 click, we can actually identify all the contact regions, and the contacts will be applied at those locations, right? So I'll show you guys later in the demo how do we detect contacts, right? So we can actually, by default, it will actually be bonding or this sliding contact. Then the user will have the capability to change them into separating contact as well. So here we are actually going into the nonlinear region, right? So here's a nonlinear run already. Next up, what the user needs to do is just define the material if it's not already defined. Find the boundary condition, right? Where is it being constrained? What's the analysis type? If this is a linear static, where are the forces and so on? And apply any solution adaptation control. So this is actually to improve the accuracy at certain areas if you need, right? Right. So now here it says that if it's not inherited from CAD. So right now, if you're reading CADs from SolidWorks, CATIA, we can actually carry over the materials. If you already define it in your CAD, we can actually carry over the materials, right, by reading the metadata and apply them accordingly. So if let's say you define steel in your CATIA and you read in the file, and we can actually read the material name steel, and if we can find the exact name in SimSolid, we will apply that material to that part, right? Otherwise, you have to define it manually yourself. Okay, so at the moment we can read JT, we can read from NX, we can read from CATIA, we can read from SolidWorks. Right? So those materials are carried over. Otherwise, you need to create your own material or define your own materials later on in SimSolid. Now, what's happening in the solving stage? Geometry evaluation is done actually in the beginning when you read the CADs in. Okay, so when you read the CAD in, SimSolid will actually generate some initial equations to represent those regions. Remember the regions, or in other words, the elements, right? So they'll create equations to represent them. And when you hit on solve, you actually go through this solution pass. So 2, 3, 4 here represents a solution pass. So the first up, they will solve the equations, right? And they'll check for stress strain recovery. Then we go on to checking for any error. We check for displacement error, we check for force error, and we also check for energy convergence, right? So once all these are met, then if the user has any solution adaptation, meaning to say special requirements at certain locations to improve the accuracy, then they'll go through this solution adaptation, right? So we will add degree of freedom equations at some constraints, also at some specific areas to increase the accuracy. Okay, so special approximation, I'll show you guys this as well later on. So by default, you actually loop here for 3 loops, right? So that's the default setting. But the user has the capability to increase this number of loops as well. So higher repetition of this will actually increase the accuracy. Excuse me. So higher repetition of this will increase the accuracy, but we will advise you not to go higher than 6 loops, right? So if you go higher than that, you probably just create noise, and you don't really see significant benefit in improving the results. So try to keep it at 6 maximum, right? And once this solution pass is done, the loops here are done, we will actually write out result functions, right? So notice the word here, functions, is not results. So we don't actually write absolute results per se. We don't actually write, for example, say the stress at this point is 100 megapascal. We don't write the absolute results. What we write is we write functions, okay? So remember that. Now here is actually a test that actually done to actually prove that the solution pass. So if you're looking at stress accuracy, increasing the solution passes will actually give you better results, right? Or more accurate results as you reach a stress convergence area. So by default is 3. So if you're looking at just stiffness, solution pass of 3 is enough. But if you're looking at stress levels, then probably you need to increase it to 4 to 6 times. Okay. And once you go higher than that, you probably just see some slight difference, but you get a really high increase of in solution time. So probably we don't need to go higher than 6. Okay. And here is actually how we improve or how do we increase the solution passes. By just increasing this number here, we can increase the accuracy. There's no need to go back to your mesh to refine your mesh or something like that, right? Now remember when I said that the SimSolid will actually write out result functions. So this is what we mean here. We will actually write result functions. So let's say it's just like a function. So let's say simple function x plus y plus z, right? With this, the user will not be able to know what is the stress level here, right? So what we actually do is after solving, SimSolid will actually create a response mesh over your part, right? So meshing is not done before solving. Meshing is done after solving, and it's only just mesh on the outer part or the surfaces of your part. So the response mesh is applied on the outer surface, and with this response mesh now, the user can go on to click at a certain point and extract what is the stress at this level, at this point, right? So the result functions are what we stored actually, and every time the user click on it, then we only give you the absolute value or the absolute stress, okay? So we don't store the results of each point here, right? We store the mesh, and then we store a separate result function. So that's why you will see our file size will be much smaller even after we solve it, right? So because we don't store the values of every point, we store a function and then we store the mesh, so the user can request for the results anytime. Okay. And due to this, response mesh is actually done just once for a single part. or for the first model, the first assembly. And we actually remember the response mesh so that the next time if you rerun this analysis or you set up another load case, but on the same model, you will realize that it solves faster the second time, right? Because we store the response mesh and rerunning it or setting up another load case and using the same model will actually give you faster results, right? So I'm just going to demo a little bit on SimSolid now. But before we go to that, here is a typical example of what's the difference in building this model in traditional finite element analysis and also in SimSolid. So let me just ask you guys this one. If let's say you're given this model here, this is actually a bus, is a roof of the bus, right? So there are about 170 parts here, about 170, or more than 170 parts. How long would it take you, or how long do you think it would take to mesh this entire model and to connect all of the parts together? 170 parts, how long will it take to mesh all of them and to connect all of them together? All right, so just want to get your feedback or your guess, right? So let's just, all right, so let me just launch this. Put your votes in. How long do you think it would take to model this bus roof? All right. No right or wrong answer. Just guesstimate. All right. So, okay, yeah. Put your votes in. Okay, closing this in 5, 4, 3, 2, 1. Right, so let me share the results. So most of you guys say 1 to 3 days. So 1 to 3 days, okay? 15% of you guys can finish in half a day. Wow, that's good. Very fast. And 15% of you guys say 1 week. So 1 week, yeah, okay. So most of you guys say can be completed within 1 to 3 days. Right. Cool. So just go back to my slides. Okay. So we asked one of our best engineers or best model build-up engineers here, and he mentioned to me that he will probably take 8 hours to complete this, right? So he said this model is quite simple. They don't have any special connections, and actually, in fact, is quite symmetrical as well. So you probably just need to take 8 hours to mesh everything and to assemble it, all right? So let me just jump to SimSolid here. All right, so yeah, most of you guys say 1 to 3 days. Fastest is half a day can be done. So I'll use SimSolid here and show you guys how can it be done in just a few minutes. Okay, so first we import the file in. So this is the bus roof. Okay, now when you import the file, you see that at the bottom it's actually checking the geometry, so it's very fast check. Then it shows me that there are some part overlaps found. So let's just zoom in and see where are there. So just, yeah. So this part here is, I think, overlapping with this part here, I think around here, right? So yeah, it's just a small overlap of 1.5 mm. So I just say ignore it first. We can connect them later on. All right. So here, just to confirm, let's see how many parts do we have. We have about 174 parts, all right? Okay. So what I do is when I read the part in, first we need to assign material because I don't have materials here defined yet. So let's say I just define steel material to all of them, apply to all parts. Okay. And next, I'll create the connection straight away. So connections, I'll do a automatic connections, searching for gap and penetration of 3 mm. I'll just increase this to resolution so that you'll manage to find all the connections. So I just increased it. And say okay, and you actually go around and search for all connections, all possible connections, right? Based on the tolerance I set, 3 mm gap and 3 mm penetration. And it managed to detect that this assembly has 2 disconnected parts. So let's just see what we are there. This is the first group, so all the parts here are connected. Okay, and this is the second group here, which is this part here. So this part is actually very short, so it probably is a mistake in design. We can still connect this part to the mainframe, but then this part is poorly designed. If I connect it forcefully, it will just create additional stiffness to the part. Right? So I just say suppress it first, not to use it for simulation. Okay. So now we just work with this group 0, this entire part here. Right. So there, connection is already done. So you don't need to mesh anything. Connection is already done in just a few minutes. So I'll set up a, say, modal analysis, right? So a free vibration, and just say find the first 10 modes, okay, and just say hit run here. So you see it passes 3 times, right? And then it plots the results, and then there, I have my results here. So it just took 7 seconds to solve this, right? And I can look at my results now. Okay, so the first 6 modes are just the rigid body modes, and then mode 7 is the real mode. Right? So you see the results here, 7, 8, right? So it's that fast. Okay, so just stop this, and it's just running on my normal PC here. Right. So in SimSolid, we just need a few minutes. Yeah. Now, what are the advanced capabilities in SimSolid? We can, as I mentioned, we have nonlinear statics. So if you want to solve separating contacts, if you want to solve nonlinear materials, we have it. You can input you can input your own stress strain curve, and we can use it for the simulation. We have geometric nonlinear as well. Okay. We can run dynamics. So let me just put my pointer. So we can run dynamics, right? Frequency response, transient response, all these are possible. We also have both pretension. So if you want to be more realistic in your design, you have both pretension, you can actually apply it here as well. And if you're analyzing the bolts, we can also plot it. We can also have this table here to give you all the bolt forces that's happening inside your bolts, right? And also, of course, the reaction forces and supports as well. Some L1 connections that we have lasers, welds, pin bushing, and in the new version, we actually have adhesive as well. So we can simulate adhesive also in the newer version. All right, so spot welds here are all available. All right, you can import from a CSV file. So if you already have the spots location in your CAD software, you can just export it out in CSV, the coordinates XYZ, and we can plot it immediately here. Or you can also do standalone spots, so you can go around the geometry and click where you want to apply the spots. Okay. All right, so SimWelds. So here is a example of SimWelds. We also have SimWelds here, and using the same example, the same bus model, the example that I used earlier. Earlier, I just used a automatic connection. Now here, I'm going to use a SimWeld connection to find all of them. Right. So I just skip the video because I'm running short of time. So basically what I've done is instead of using the automatic connection earlier on, I just changed it to SimWeld, and also using a very simple search function in SimSolid, I'll just search the entire model for possible areas to weld as well. If you do not have the weld lines already, you can simply just use this very quickly, right? So now we move on next to product verification and validation. So most of the time people say, "Wow, this is fast," but is it accurate, right? So here we have done some testing to prove that it's accurate, right? This is a chassis here, and you can see that it consists of about 70 parts in the CAD. And if you want to represent this in the traditional finite element analysis, we are meshing this with 1.1 million second order tetra to improve the accuracy, right? And you can see that between SimSolid and the traditional FEA, you can see that we actually get pretty close results, right? We comply pretty good with the traditional finite element method, right? So this is a model analysis. You can see that we match pretty good. And in terms of displacement or in terms of stiffness, you can see that in SimSolid, we get the maximum displacement here is about 1.36. When we run it with the second order tetra, we usually get 1.41. So pretty good margin of error here as well. Right. And here, of course, we just increase the solution passes to 6 times. Here we need to mesh with a second order 1.1 million tetra. Now, if you're looking at stress, this is another example here for stress levels, comparing the major principal stress for both. You can see, not sure if you can see it here clearly. In SimSolid, the highest stress here is about 54 megapascal. We get the same result here as well. Okay. Another example here, this is a golf driver or golf club. So you can see here, golf driver is generally very complex geometry because it's actually consisting of non-uniform thickness, and it's very thin wall. So it's very thin and it's non-uniform. So it will be hard to mesh this with shell elements. If you're meshing it with tetra elements, you're going to have very small tetra, right? So that's the challenge if you're doing this in the traditional finite element method. So here, comparing the results in SimSolid, we get our mode 7 here at about 2000 hertz, right? Same thing, we see the same results here in the traditional finite element analysis. Okay, and here you see that just to compare, give you guys a comparison. This is a very large chassis here, and it's represented with 1.1 million second order tetra, right? And this is just a very small golf driver here, and we represent this with 1.93 million. Right? So the number of elements here is higher than the entire structure here. Right? So imagine how long will it take to solve this one. Okay. So comparing the results, you can see the percentage of difference between both the solvers. So SimSolid and the traditional finite element analysis, you can see that we have a very small error of differences here, right? And comparing the speed of simulation to prepare the model, SimSolid can just be done in 1 minute, because once you read the CAD in, you apply the material, it's just one part, so there's no connection or anything. So it's very fast. Then in the traditional refinement method, you need to mesh it with very good second order tetra elements, right? So you take probably longer time to simplify the geometry. You cannot just mesh everything, you need to simplify it, right? Simplify all your fillets and so on. So that's why you need longer time to prepare the model. Okay, and to solve it, because of the such high number of elements to solve, you probably take longer here. Okay, so the total time, you can see 10 minutes compared to 2.5 hours. That's how fast you get your results. Right? If you're not convinced by these few examples here, I actually shared out some handouts, right? So the first handout is a solution verification. This is done with simple models, so your cantilever beams and so on. Those simple geometry, we compare them, right? And you can look at the results there. There's another stress validation. This is based on actual parts, so you see real world. So these are not just simple cantilever beams, they're actual parts, actual objects. And this is actually not done by us. This is done by Richard King, which is a co-founder of Creo Simulation, right? But right now he's an independent engineer, so he helped to compare this, compare SolidWorks and also SimSolid. So he used SolidWorks because SolidWorks can also perform simulation, and he's comparing a converged solution here. So for SolidWorks, he needs to refine the mesh a few times to achieve mesh convergence. Then he used that result to compare it with SimSolid. SimSolid, how do we increase the accuracy? By just increasing the solution passes. Okay, so it's that simple to increase accuracy in SimSolid. So you can go through this handout as well. I've sent to you guys. Look at the examples being compared, and you can see we actually have a very good agreement with the traditional finite element analysis here. Okay, and the last handout is actually a benchmark done by NAFEMS, right? So if you're not sure, if you're not heard of NAFEMS, NAFEMS is a neutral body, right, that promotes finite element method, right? So they are not citing to any solvers, they are not citing to any companies, so their benchmark can be considered as a very neutral opinion, right? So you can go through this as well, this benchmark, and you can see that we actually get pretty good accuracy also with the traditional finite element analysis. So the same thing, NAFEMS ran a series of objects with different load cases, and they compare a solution from mesh convergence result against SimSolid as well. Now, right now, I would like to introduce you guys to why is it so beneficial to use SimSolid in the very beginning stage of your design. So why is it so good to use SimSolid in your concept design stage? That's because we have we help you guys perform better, get results faster with design studies here, right? So imagine that the designers come up with a few designs, and you're supposed to analyze them or give the structural performance of the designs, right? Let's say we start off with just this design one, the initial design. So you go to your, let's say you go to your traditional finite element solver. Before that, you need to mesh this part first, right? And then you solve it. Then the designer gives you a new part, right? Maybe the first design here, there are some high stresses. So you suggest to the designer, this design is not good. Then the designer come up with a second design. Second design where there are some bits here to improve the design. Then again, you need to go back and mesh this part. Okay. Then you produce the result, and then you feedback to the designer. The designer decides, okay, it's still not very good. I'll come up with a third design here where I add this brick at the bottom. Then you go back to the preprocessor to mesh this part again before you can actually solve it. Okay. And I'll show you guys here in SimSolid, you can actually do all this in very short time, because we tend to reapply the existing material properties, the connections, and all the load case setup that we've done from the first design to the second and third design as well. Right. So I'll just clean it up in SimSolid. So this is the short tower design. Okay. So the design one, read it in, right? Okay, this is just a single part. So no matter if it's a single part or if it's a very large assembly, you can use SimSolid for this. So let me just set it up first. No materials here, I'll just apply a aluminum material. Okay, so there's only one part. There's only one part, so I don't need to do any connections. Straight away, I go and create my structural analysis. And I will apply a constraint at the holes here to simulate where is it being bolted. All right. Okay. Okay, good. Right, then next, this is the constraint. I will apply say a remote load, okay, at this here to simulate the force that is being sustained on this part. And let me just put, say, negative because it's upwards, okay, and about 20 kilonewton. Right, so this is the force and those are the constraints. And then let me just run this. So before I run that, here is where we actually increase the accuracy. If you're looking at stresses, then probably we'll increase this to adapt for stress. Or you can also choose the default adapt for stiffness. Right, so adapt for stress will actually run an extra pass for accuracy. But for time's sake, I'll just put adapt for stiffness so that it runs faster. There isn't very much difference, but let's just do adapt for stiffness here. All right, so you see, evaluates the geometry, 3 passes, 1, 2, 3, and plotting the results. Okay, so then you can go and check what's the stress here. Okay, 1 is the stress, high stress is there. Use this to immediately see where's the high stress. Okay, and then so minimum stress here, and then high stress. Okay, so let's say this is where you're looking at. Just do bookmark. Okay, and let me just rename this so that it's easier to identify. Say this is stress. And now if you're also looking at displacement or the stiffness, you can also look at displacement as well. So maximum displacement about 0.7 here. I'll just do another bookmark and rename this as displacement. All right, so this is the first design. Now you go back to with this stress result, you go to your designer and you say, okay, the stress is very high, let's just try to reduce this. So he comes up with a second design. Okay, read it in. All right, so you see all the constraints are automatically carried over from the first design and applied on the second design. Right, so the constraints are here, the forces are applied as well, and material is not carried over, so what I need to do is just assign again the material, so aluminum. Okay, then what's next? Just hit run. Okay, so you see the second design has beads here to stiffen this part here, stiffen this area. Okay, done. So to look at the second result, I can just click on this bookmark here. Right, so this is the bookmark that we have saved for the first design. First design here is about 750 megapascal. Second design, we managed to reduce this to 483 or 480 megapascal. Right, stiffness wise, this is the first design, 0.7. The second design, click on here, and you see stiffness is higher here. So displacement has reduced. Okay, but stress For the second design, it's still high. So let's say you go back to a designer, say it's still very high. Then designer comes back with you with a third design. Okay, just read the third design in. Now, third design here, you see there's a longer ribs here at the bottom. Then now you see again the constraints and forces are carried over. Likewise, I'm just gonna assign the same material. Okay, and then hit run. Okay. So 3 passes and then plotting the results. Done. So jump back to your bookmark. Okay, this is the first design. And this is the high, this is the stress. And then this is the final design here. So you managed to reduce this to 70. So using the bookmark and just jumping between the results of design 1, design 2, and design 3, you can actually look and compare all these results here. Right. Likewise, with the displacement, this is the displacement. There's bookmark for the first design, a 0.7. Final design managed to reduce this to, well, less than 0.1. Right. So this is the benefit of using a SimSolid here for design studies. You can have multiple designs, right? With all the designs in, SimSolid will automatically carry over all the loads. And if there are connections, they'll carry over all the connections as well. Connections, loads, and also the forces, everything is carried over, right? And all you need to do is just, after you read the new design in, just hit run, and you get to compare the results straight away. Okay, so that's the benefit of using SimSolid for design studies. So you can compare, you can evaluate as fast as you design it. So some of the customers who have been using SimSolid, Renault here has been using SimSolid for the design of their subframe, right? So in traditional finite element analysis, subframe requires a lot of special care in meshing, especially at those weld areas, right? So with with the simple workflow in SimSolid, the welds are identified automatically, and we can actually connect all the parts together in just a few minutes. Okay, so they managed to reduce their development time, right? From let's say, yeah, about, to build the model, they require 1,000 over minutes, right? So that's about a few days, right? And they managed to reduce this in just no time, right? So lead time reduction from 25 to 100 times. And they managed to maintain accuracy while doing that, okay? So if you can get accurate results in a very short time, why don't you just use that method, right? Why do you still want to keep to the traditional way of doing things, right? So this is the paradigm shift that we need to experience, okay? Now here is another example from CNH Industrial. So they are trying to find root cause to this problem here. So when they have done testing, they realized that they actually found some cracks here. Okay, so they try to use SimSolid to find out if we can predict the location. It's a non-linear analysis, and there are some bulk pretensions as well. So bulk pretensions, and there are about 157 contacts for this entire wheel assembly here. Okay, so we managed to predict this in just less than 2 hours virtually, right? So from once they get the test done, they see, oh, something is appearing here. They go to SimSolid and they just work everything out within 2 hours. They find the same thing, right? So we predicted the same high stress at these locations as well, right? Then we can actually, then we can do some modification and know where to actually countermeasure the problem, right? So with SimSolid, we can actually help you to design faster. We can help you to explore more possibilities, and of course, the ultimate goal is to boost productivity. Okay. Right, so that comes to the end of my presentation. If you have any questions, type in the chat box, or you can raise your hand. I will unmute you guys if you guys want to talk to me. Okay, let me just go through the questions first. Okay, I'll just put all your hands down and so that I can filter better. If you have any questions, just raise your hands now so that I can see it. Okay, I see a hand here. Dr. Musab, I'm going to unmute you.
Okay, good morning.
Morning.
I just want to ask about how to get the software, complete software, how much we need to pay, and how to download it.
Okay.
This is for me using this software.
Yep. So I got your question. So you're asking how much is this and where can we download it, if I get it correctly?
Okay.
Right. So I'm not going to talk the price here, so we will take it offline. But for trial, you can actually log on to this altair.com/SimSolid for your free trial, right?
Okay.
If you want to know more details about this, you can actually contact me as well. So I'll give you guys my email, and if you guys want to have a some question that you want me to answer privately, I can also email you guys.
If I want to get more video for training, how I can get it?
Yeah, so we actually conduct trainings before the lockdown or before this COVID-19. We actually conduct trainings at our office, but now because we're not all in lockdown, so if you guys are interested to know more about SimSolid, and you guys interested to have a online virtual class on SimSolid, just type class on the chat box, and if there are enough requests, I'll conduct another session on how do we use SimSolid live. Okay, so if you're interested, just type class in the chat box, and we will consider to have another online session on SimSolid. All right.
Okay. Thank you.
All right. Thank you. So let me see. Let me go through the questions. Is it compatible to lower version of SolidWorks at 2015? Yeah, actually, yeah. Lower version shouldn't be a problem unless it's the newer one that we need to upgrade our CAD reader. So older versions are usually okay. So just for information, SimSolid was previously a add-on on SolidWorks. There's actually a button there you can actually click and you can actually launch directly SimSolid. But because now Altair has already acquired SimSolid, so that's why it's no longer available. But yes, we work very well with SolidWorks. What is the minimum system requirement for SimSolid? We recommend you to have at least 8 CPU, right? Recommend you to have at least 8 CPU and at least 16 gig RAM, right? So 8 CPU and 16 gig RAM. Graphic cards is not necessary. We just need an OpenGL of 3.2 or 3.3 is enough. But more requirement on the number of CPU. We can also still work with 4 CPU. I've tried with four CPUs before, and it still work fine. But the RAM there is important. So at least 16 gig RAM, I recommend. Another question, can it repair unstitched surface automatically? No, not in SimSolid. So in SimSolid, if you notice, there's actually no geometry modification tools. So if you want to repair any surfaces, you want to repair any CAD geometry, you need to go back to your CAD software, or you can actually use another software of ours, which is Inspire, where we can actually repair damage or bad surfaces, right? So you can actually go to Inspire to do that. And in the new version of Inspire, Inspire 2019.4, we actually embedded the SimSolid solver into Inspire. Okay, so if you're interested to know more about that, you can also email me on that. But we also have already the SimSolid solver in Inspire. Right? But it's two separate things. I'm not going to confuse you about it, right? Can we do explicit simulation? No, not at the moment. It's still in the region of implicit. How frequent is SimSolid being used in industry? We have very good usage already in Thailand. So there's actually a auto parts maker in Thailand that's using SimSolid daily, right? And globally, we have a lot of those big car makers that they are using SimSolid. As I mentioned, Renault is already using SimSolid. So yeah, some other companies, even the aircraft OEMs, they're also exploring SimSolid. Right. Is there any optimization tool? No, we cannot optimize in SimSolid. If you're looking for optimization tools, I will recommend you to look at Inspire. Okay. Any plan to add hyperelastic material? Yes, it has always been in our mind, but not at the near future. Right? Not in the near future. Okay. Right. So if you have any more questions, just type it in the chat box. In the meantime, I'll launch another poll here just to get a few of you guys. So after listening to what I have on SimSolid, what we can do in SimSolid, tell me what would be your main interest if you were to use SimSolid. So what interests you the most on SimSolid? So this is a multiple answer. You can check those that are relevant to you. Another question is there any way to improve accuracy other than increasing solution paths? Yes, there is. There are some other methods. We can actually turn on some additional functions, but I'll cover that if we are going to have another class. So yes, we have other ways to improve accuracy, not just by the solution passes. Another question is anisotropic material? No, we are only working with isotropic material at the moment. All right, so I'll close this poll now. Okay, so most of you guys are looking forward to the iterations and design studies here. Okay, and also the faster time to market. Good. Okay, so having said that, I know SimSolid is kind of new to you guys. So let me launch another poll here. What would be your biggest hesitation to use SimSolid? Right, so there is another question. Is SimSolid going to replace traditional finite element analysis? No. Again, it's not here to replace the traditional finite element analysis. You still need that. For example, let's say if you're going to do explicit, if you're going to do non-linear, very non-linear solution, you still need the traditional finite element methods. But SimSolid is here to complement them. So the simulation doesn't need to be done at the very end. It can be done at the beginning designing stage. So that's the best way, that's the best time to use SimSolid, right? So use SimSolid to get rapid feedbacks to your designers to know where to fix before you actually perform a actual or a full simulation, right? Another question, any other plan to implement fatigue calculation to SimSolid? Yes, there is also a plan for that, but again, not in the near future. Another question, can we reuse the model from SimSolid in other explicit solver? I don't get you what you mean reuse the model. So if you are talking about you want to analyze the model, then you probably would need to mesh it again, right? So let's say you have already, for the design tower, the shock tower example just now, let's say you're satisfied with design tree, then you probably need to send this design tree to the simulation team and they need to mesh it up for the explicit solver, right? So it's a separate workflow. Certification service. No, we don't have any certification service with SimSolid here. Right, okay, so I'll just close the poll and let me just share this. So 60% of you still do not understand how it works, okay? So even for me, I do not understand how it works, but I just know that it's actually an extended version of finite element analysis. So you don't have to worry about how it actually works in the background, right? For example, let's say if you're driving a car, do you exactly know how it works, right? So you're just going to use the car, right? You're just going to drive the car. You don't really go and understand what will happen if I start the engine, how much fuel is being pumped into, what's the ratio between the fuel and oxygen and so on. So you don't need to really understand every single thing, just as long as you can use it to improve your design. You can use it to improve your workflow. Then why so hesitant to use it, right? So in a nutshell, if let's say I would strongly encourage you guys to just try SimSolid, right? Maybe if you're interested to have a class, then we can have a class after you attended my class. Go back and try on your actual products, right? If it works for you, then why not just use SimSolid, right? So don't really have to understand the technicality behind it, as long as it can give you accurate results in a very short time. Don't say no to SimSolid, right? So just use it. And if you encounter some problems later on, if you have tried SimSolid and you found out that it's not really that accurate, and you probably want to like chuck it aside, don't do that, right? If you encounter any problems, come back to me. You can always email me and I'll be happy to help you guys to adopt SimSolid into your workflow, right? Right, so I guess that is all for today. I don't see any questions. Let me see if you have any hands. Right, so that's all for today. Thank you guys for joining this session. I hope you guys learned something. Again, if you are interested to join the class, just type class in the chat box, and I will probably, if there are enough requests, I'll probably have another session to introduce the workflow of SimSolid in detail, so you guys will actually get a hands-on feel on how to use SimSolid. Good. Right. So thank you guys for joining this session. Hope you guys are safe at home and take care. Bye-bye.